Welcome to the Nocturnal Astronomer, where we explore the gentle mysteries of our universe under the cover of darkness. I'm your host, Atlas Reed, and tonight we're embarking on a serene journey through the cosmic cradles where stars are born. Picture vast clouds of gas and dust stretching across light years of space, slowly stirring and swirling in an ancient dance that has continued for billions of years. These are stellar nurseries, the peaceful birthplaces where gravity works its patient magic, gathering material grain by grain until new suns ignite in the darkness. Tonight, we'll drift through the Eagle Nebula's towering pillars, witness the delicate ballet of molecular clouds, and understand how the smallest disturbances can trigger the formation of entire stellar families. Let's dive in. In the vast expanse between stars, enormous clouds of gas and dust drift through space like celestial cotton candy. These molecular clouds, as astronomers call them, are the fundamental ingredients for star formation. They contain primarily hydrogen, the universe's most abundant element, mixed with traces of helium and heavier elements forged in the hearts of previous stellar generations. These clouds are truly immense. A typical molecular cloud might span 50 to 300 light years across and contain the mass of 10,000 to 10 million suns. To put this in perspective, imagine a cloud so large that light, traveling at 186,000 miles per second, would take centuries to cross from one side to the other. Yet despite their enormous size, these clouds are incredibly tenuous, with densities far lower than the best vacuum we can create on Earth. The temperature within these stellar nurseries hovers around 10 to 20 degrees above absolute zero, making them among the coldest places in the universe. At these frigid temperatures, atoms move sluggishly, and molecules can form more easily. Water, ammonia, methanol, and dozens of other compounds freeze onto tiny dust grains, creating microscopic snowflakes that drift through the cosmic void. These dust particles, though minuscule, play a crucial role in star formation. Each grain is smaller than the particles in cigarette smoke, yet they serve as shields, protecting the cloud's interior from the harsh radiation of nearby stars. This protection allows the gas to cool even further and begin the slow process of gravitational collapse. The Orion Nebula, visible to the naked eye as a fuzzy star in the constellation Orion, represents one of the most studied stellar nurseries in our galaxy. Located about 1,300 light-years from Earth, this glowing cloud of gas and dust spans roughly 24 light-years and contains enough material to form thousands of new stars. Within the Orion Nebula, astronomers have identified dense cores where star formation is actively occurring. These cores, typically a few light-years across, contain several times the mass of our Sun concentrated into a relatively small volume. As we'll explore in our journey, these dense regions are where the magic of stellar birth truly begins. The beauty of stellar nurseries extends beyond their scientific importance. When viewed through telescopes, these cosmic clouds reveal intricate structures painted in ethereal colors. The red glow comes from hydrogen gas energized by nearby young stars, while blue regions often indicate reflected starlight bouncing off dust particles. Dark lanes and cavities carved by stellar winds create dramatic silhouettes against the glowing backdrop. The process of star formation within these nurseries unfolds over millions of years, a timescale that dwarfs human civilization but represents merely a moment in cosmic history. Understanding these processes helps us comprehend not only how stars form, but also how planetary systems, including our own solar system, came into existence billions of years ago. Gravity, the weakest of nature's four fundamental forces, becomes the dominant sculptor in the quiet realm of molecular clouds. Unlike the dramatic explosions and violent collisions we often associate with space, star formation begins with the gentlest of touches. Imagine gravity as a patient gardener, slowly gathering cosmic seeds over millions of years. Within a molecular cloud, gravity works constantly to pull every particle toward every other particle. However, this attraction is incredibly weak when dealing with such diffuse material. A single hydrogen atom in a molecular cloud experiences gravitational forces billions of times weaker than what we feel standing on Earth's surface. Yet given enough time, these tiny tugs accumulate into something profound. For gravity to overcome the natural tendency of gas to expand and disperse, the cloud must reach a critical threshold known as the Jeans mass, named after physicist James Jeans, who first calculated this relationship in 1902. Think of it like a cosmic tipping point. Below this mass, the cloud's internal pressure and turbulent motions keep it stable. Above this threshold, gravity gains the upper hand and collapse begins. The Jeans mass depends on both temperature and density. Colder clouds have lower Jeans masses, meaning they can begin collapsing with less material. This is why the frigid temperatures in molecular clouds are so important. At 10 degrees above absolute zero, a cloud needs only about 1 solar mass of material concentrated in a region roughly 1 light year across to begin gravitational collapse. But molecular clouds rarely exist in perfect isolation. They're stirred by various disturbances that can trigger or accelerate star formation. Shock waves from nearby supernovae, the gravitational influence of passing stars, or collisions between clouds can create density enhancements that push regions over the Jeans threshold. The Eagle Nebula, made famous by the Hubble Space Telescope's Pillars of Creation image, demonstrates this process beautifully. The towering columns of gas and dust are being sculpted by intense radiation from nearby massive stars. As this radiation evaporates material from the pillar surfaces, it reveals denser knots within that are actively forming new stars. Once gravitational collapse begins, it proceeds slowly at first. The initial contraction of a molecular cloud core takes roughly 100,000 years, a mere blink of an eye in cosmic terms, but still longer than all of human history. During this phase, the cloud remains nearly transparent, and its temperature stays constant as heat radiates away into space. As the cloud contracts, its gravitational field strengthens, accelerating the infall of material. Particles that started light years apart gradually spiral inward, following paths determined by the cloud's rotation and magnetic field. This process resembles water circling a drain, but stretched across distances that dwarf our solar system and timescales that span geological ages. The magnetic fields threading through molecular clouds add another layer of complexity to this cosmic choreography. These fields, though incredibly weak by terrestrial standards, can support the cloud against gravitational collapse for extended periods. Only when the magnetic field lines become sufficiently tangled or when the density increases enough to overwhelm magnetic support can collapse proceed unimpeded. As gravitational collapse continues, the once diffuse molecular cloud core begins its transformation into something more recognizable as a stellar precursor. This marks the birth of a protostar, though it bears little resemblance to the brilliant suns we see shining in our night sky. Instead, imagine a cosmic cocoon, hidden within layers of dust and gas, slowly awakening to its stellar destiny. The collapse accelerates as the core becomes denser. Material falls inward at speeds reaching several kilometers per second, carrying with it the angular momentum of the original cloud's rotation. Just as a figure skater spins faster when pulling in their arms, the contracting core begins to rotate more rapidly. This rotation prevents all the material from falling directly onto the central object, instead forming a flattened disk around the growing protostar. These circumstellar disks, also called protoplanetary disks, are where planets will eventually form. The disk serves as a cosmic conveyor belt, gradually feeding material onto the central protostar while providing the raw ingredients for future worlds. Our own solar system formed from such a disk roughly 4.5 billion years ago, making these structures particularly fascinating to astronomers seeking to understand planetary formation. The protostar itself remains hidden behind thick veils of dust during its early development. The infalling material heats up as it approaches the central object, but this heat is quickly absorbed and re-radiated by surrounding dust grains at much longer infrared wavelengths. To optical telescopes, the protostar remains invisible, detectable only through its infrared glow and the effects it has on surrounding material. During this embedded phase, which lasts roughly 100,000 years, the protostar grows primarily through accretion. Material from the surrounding disk spirals inward, releasing gravitational potential energy that heats both the disk and the central object. The protostar's surface temperature rises to several thousand degrees, hot enough to glow red if we could see through the obscuring dust. Not all the infalling material reaches the protostar's surface. Some is ejected in powerful bipolar jets that punch through the surrounding envelope at speeds of hundreds of kilometers per second. These jets, guided by magnetic fields, carry away excess angular momentum and help regulate the accretion process. The Herbig-Haro objects scattered throughout star-forming regions are shock waves created when these jets collide with surrounding gas. The protostar's internal structure during this phase resembles a layered onion. At the center, temperatures and pressures rise steadily but remain far below the levels needed for nuclear fusion. The core consists of molecular hydrogen slowly dissociating into atomic form as temperatures climb above 2,000 degrees. Surrounding layers contain a mixture of gas and dust, with the outer envelope still cold enough for molecules to survive. As the protostar continues to accrete material, its central temperature and pressure inexorably increase. The object becomes fully convective, meaning hot material from the interior rises to the surface while cooler material sinks inward. This convection efficiently transports heat throughout the protostar, maintaining a relatively uniform temperature gradient. The protostar phase represents a delicate balance between gravitational collapse and internal pressure. Unlike main sequence stars, which derive their energy from nuclear fusion, protostars are powered entirely by gravitational contraction. As the object shrinks, gravitational potential energy converts to heat, keeping the protostar warm and preventing further rapid collapse. After hundreds of thousands of years hidden within its dusty cocoon, the young protostar begins to assert its presence more dramatically. The surrounding envelope of gas and dust that once completely obscured the forming star starts to thin and disperse, marking the beginning of a crucial transition phase in stellar evolution. This clearing process occurs through several mechanisms working in concert. The protostar's increasing luminosity heats the surrounding dust, causing it to radiate energy and gradually evaporate. Stellar winds, streams of charged particles flowing outward from the protostar's surface, push against the remaining envelope material. Meanwhile, the powerful jets we discussed earlier continue to carve cavities through the surrounding medium. As the envelope clears, astronomers can finally observe the protostar directly at optical wavelengths. What emerges is a T Tauri star, named after the first example discovered in the constellation Taurus. These young stellar objects are characterized by their variability, strong stellar winds, and the presence of circumstellar disks. They represent stars in their cosmic adolescence, no longer hidden infants but not yet mature main sequence stars. T-Tauri stars are remarkably active compared to older stars like our Sun. Their surfaces are covered with enormous magnetic field loops that can extend several stellar radii into space. These magnetic fields accelerate charged particles, creating powerful stellar winds that flow outward at hundreds of kilometers per second. The interaction between these winds and the surrounding material creates beautiful shock fronts visible in telescope images. The circumstellar disk plays a crucial role during this phase. While the star continues to accrete material from the inner disk regions, the outer portions begin the slow process of planet formation. Dust grains stick together through electrostatic forces, gradually building larger and larger aggregates. Over millions of years, these dust bunnies grow into pebbles, then boulders, and eventually planetesimals large enough for gravity to take over. The disk structure becomes increasingly complex as the young star evolves. Gravitational instabilities create spiral arms and gaps, while magnetic fields channel material along specific pathways. The inner regions, heated by the central star, become a realm of rocky materials, while the outer, cooler zones harbor water ice and other volatile compounds. During this phase, the young star's energy output comes from a combination of continued gravitational contraction and the accretion of disk material. The star has not yet reached the temperatures and pressures necessary for sustained nuclear fusion, so it continues to slowly shrink under its own gravity. This contraction releases energy that keeps the star shining, though much more dimly than it will during its main sequence lifetime. The clearing of the stellar nursery is not uniform or instantaneous. Different regions of the original molecular cloud core disperse at different rates, creating complex, evolving structures. Some material may linger in the system for millions of years, while other regions clear relatively quickly. This uneven process creates the beautiful, intricate shapes we observe in young stellar objects and their surrounding nebulae. Observations of nearby star-forming regions like the Taurus molecular cloud have revealed populations of T-Tauri stars at various stages of this clearing process. Some remain heavily embedded and detectable only at infrared wavelengths, while others have emerged as visible stars surrounded by thin, nearly transparent disks. This diversity allows astronomers to study stellar evolution as if watching a time-lapse movie of star formation. Deep within the contracting protostar, a momentous transformation approaches. For millions of years, the young star has derived its energy solely from gravitational contraction, slowly shrinking and heating as it converts potential energy into thermal energy. But as the core temperature climbs toward 10 million degrees, the star approaches the threshold for nuclear fusion, the process that will power it for billions of years to come. The journey to nuclear ignition is gradual and inevitable. As the protostar continues to contract under its own gravity, the atoms in its core are squeezed ever closer together. At temperatures below 10 million degrees, the electrical repulsion between positively charged hydrogen nuclei prevents them from approaching close enough to fuse. But as thermal energy increases, a small fraction of nuclei gain enough speed to overcome this electromagnetic barrier. The first nuclear reactions occur sporadically, like scattered sparks before a fire catches. Individual hydrogen nuclei, moving at tremendous speeds due to the extreme temperature, occasionally collide with enough energy to fuse together. These initial reactions release energy and helium nuclei, but the rate remains too low to significantly affect the star's energy balance. Think of this process like trying to start a campfire with damp wood. The first few sparks may catch briefly but quickly die out. Only when enough heat builds up does the fire become self-sustaining. Similarly, the star must reach a critical temperature where nuclear reactions generate enough energy to maintain the conditions necessary for continued fusion. The specific nuclear process powering stars like our Sun is called the proton-proton chain. In this sequence of reactions, four hydrogen nuclei ultimately combine to form one helium nucleus, releasing energy in the form of gamma rays and neutrinos. The gamma rays are gradually absorbed and re-emitted by the stellar material, eventually reaching the surface as visible light. The neutrinos, barely interacting with matter, stream directly out of the star at the speed of light. When nuclear fusion finally becomes self-sustaining, typically when the core temperature reaches about 15 million degrees, the star undergoes a fundamental change in character. The energy generated by fusion creates an outward pressure that exactly balances the inward pull of gravity. This equilibrium marks the star's arrival on the main sequence, the stable phase that will dominate most of its lifetime. The transition to main sequence status doesn't happen overnight. The star must adjust its structure to accommodate the new energy source at its core. Convection patterns change, the stellar atmosphere settles into a more stable configuration, and the violent variability characteristic of T-Tauri stars gradually subsides. This adjustment period can take several million years for stars like our Sun. The newly ignited star's appearance changes dramatically during this transition. The chaotic brightness variations of the T-Tauri phase give way to steady, reliable energy output. Strong stellar winds diminish as the star's magnetic field becomes more organized. The circumstellar disk, no longer fed by active accretion, begins its final evolution toward a mature planetary system. Nuclear ignition also marks the beginning of the star's long-term evolution. The fusion of hydrogen into helium in the core gradually changes the star's internal composition and structure. Over billions of years, this process will drive the star through various evolutionary phases, ultimately determining its final fate as a white dwarf, neutron star, or black hole. For stars with masses similar to our Sun, the main sequence phase lasts approximately 10 billion years. More massive stars burn through their nuclear fuel much more quickly, existing fast and dying young in cosmic terms. The most massive stars may exhaust their hydrogen fuel in just a few million years, while the smallest red dwarf stars can continue fusing hydrogen for trillions of years. Most stars are not born alone. The molecular clouds that serve as stellar nurseries typically fragment into multiple dense cores, leading to the formation of stellar clusters containing dozens, hundreds, or even thousands of young stars. These cosmic families, born from the same parent cloud, share similar ages and chemical compositions while displaying a fascinating range of masses and evolutionary paths. The process of cluster formation begins during the initial collapse of a molecular cloud. Rather than contracting uniformly, the cloud develops density fluctuations that grow over time. Turbulence within the cloud creates a complex web of filaments and knots, each potentially capable of forming one or more stars. Computer simulations of this process reveal intricate, branching structures resembling cosmic river deltas or neural networks. As individual cores within the fragmenting cloud begin their own gravitational collapse, they compete for the available material. Cores that start with slight advantages in mass or density can grow more rapidly, sometimes capturing material that might otherwise have formed individual stars. This competitive accretion helps explain why stellar clusters exhibit such a wide range of stellar masses. The Pleiades, visible to the naked eye as a tight grouping of bright blue stars in the constellation Taurus, represents a beautiful example of a young stellar cluster. Located about 440 light-years from Earth, this cluster contains over 1,000 stars formed from the same molecular cloud roughly 100 million years ago. The brightest members are hot, massive stars that shine with brilliant blue-white light, while fainter red dwarf stars make up the majority of the cluster's population. Open clusters like the Pleiades are loosely bound by gravity and gradually disperse over hundreds of millions of years. As the cluster orbits through the galaxy, gravitational encounters with other stars and molecular clouds slowly strip away members. Eventually, the cluster dissolves completely, leaving its former members scattered throughout the galactic disk as field stars. More tightly bound are globular clusters, ancient stellar cities containing hundreds of thousands to millions of stars packed into spherical volumes just tens of light years across. However, these represent a different population of stars, formed during the early history of our galaxy when conditions were quite different from those in present-day stellar nurseries. The formation of stellar clusters has profound implications for planetary system development. In the dense environment of a young cluster, gravitational interactions between stars can disrupt planetary formation or strip away newly formed planets. Close encounters might scatter comets and asteroids, potentially delivering water and organic compounds to inner planets or, conversely, removing these materials entirely. Binary and multiple star systems are common products of cluster formation. When two or more protostars form close together, they can become gravitationally bound, orbiting around their common center of mass. Roughly half of all stars in our galaxy are members of binary or multiple systems, making our solitary sun somewhat unusual. The study of stellar clusters provides crucial insights into star formation and early stellar evolution. Since all members of a cluster formed at essentially the same time and from the same material, differences between cluster stars reflect primarily their different masses. This allows astronomers to test theories of stellar evolution by observing stars at various stages of development within a single cluster. Young clusters also serve as laboratories for understanding the initial mass function, the distribution of stellar masses produced during star formation. Observations consistently show that low-mass stars vastly outnumber high-mass stars, with the most massive stars being extremely rare. This pattern appears universal, suggesting fundamental physical processes govern how molecular clouds fragment and form stars. The dispersal of stellar clusters plays an important role in galactic chemical evolution. Massive stars in young clusters exist brief but spectacular existences, ending in supernova explosions that scatter heavy elements throughout the surrounding interstellar medium. These enriched materials become incorporated into future generations of stars and planets, gradually increasing the metallicity of the galaxy over cosmic time. As we reach the end of our peaceful journey through stellar nurseries, it's worth reflecting on the profound cyclical nature of star formation. The process we've explored, from the initial stirring of molecular clouds to the nuclear ignition of newborn stars, represents just one movement in a cosmic symphony that has played for billions of years and will continue for billions more. The stars born in these nurseries will themselves become agents of change in the galaxy. The most massive among them will exist spectacular but brief existences, fusing hydrogen into helium, then helium into carbon, oxygen, and heavier elements in their cores. When these stellar giants exhaust their nuclear fuel, they'll explode as supernovae, blasting their enriched material back into the interstellar medium at tremendous speeds. These supernova shock waves serve multiple purposes in the galactic ecosystem. They heat and stir the interstellar gas, creating the turbulence that helps trigger new episodes of star formation. They also enrich the gas with heavy elements forged in stellar cores, providing the raw materials for rocky planets and, ultimately, biological processes. Every atom of carbon in our bodies, every molecule of oxygen we breathe, was created in the nuclear furnace of a star that existed and died before our sun was born. Even stars like our sun, too small to explode as supernovae, contribute to this cosmic recycling. During their final evolutionary phases, they'll puff off their outer layers as planetary nebulae, returning roughly half their mass to the interstellar medium. These gentle stellar exhalations carry the products of nuclear burning back to the galactic community, ready to be incorporated into future stellar generations. The molecular clouds themselves are not permanent features. Over timescales of tens of millions of years, they form, evolve, and disperse. Some are disrupted by the very stars they create, as stellar winds and radiation gradually erode the parent cloud. Others are torn apart by galactic tidal forces or collisions with neighboring clouds. Yet new molecular clouds continuously form from the cooling and condensation of hot interstellar gas. This eternal cycle connects us intimately to the cosmos. The calcium in our bones was forged in the core of a dying star. The iron in our blood was created during a supernova explosion. The water we drink contains hydrogen atoms that may have drifted through multiple molecular clouds before becoming part of the disk from which Earth formed. We are, quite literally, made of star stuff. Modern astronomy continues to refine our understanding of stellar birth through increasingly sophisticated observations and computer simulations. Space telescopes like Spitzer and Herschel have peered through dust clouds to reveal protostars in their earliest stages. The Atacama Large Millimeter Array has mapped the intricate structures of protoplanetary disks with unprecedented detail. Future missions will undoubtedly reveal new aspects of this ancient process. Perhaps most remarkably, the formation of stars and planets appears to be a common, even inevitable, consequence of the laws of physics operating in our universe. Wherever we find the right conditions of gravity, temperature, and density, stellar nurseries emerge. This suggests that the cosmos is filled with worlds, some perhaps harboring biological processes that, like us, are composed of elements forged in stellar cores and wondering about their place in the universe. The gentle processes we've explored tonight, playing out over vast scales of space and time, remind us of our connection to something far grander than our daily experience suggests. In the quiet darkness between the stars, new suns are always being born, continuing a story that began billions of years ago and will continue long after our own star has faded to a cold white dwarf. And on that note, we conclude our serene voyage through the stellar nurseries where baby stars are born. We've drifted through molecular clouds vast beyond imagination, witnessed the patient work of gravity as it gathers cosmic dust into newborn suns, and observed the eternal cycle that connects every atom in our bodies to the nuclear furnaces of distant stars. From the initial stirring of gas and dust in the depths of space to the moment when nuclear fusion ignites in a protostar's core, we've followed the gentle transformation that turns the simplest ingredients into the brilliant lights that illuminate our night sky. These processes, unfolding over millions of years across distances measured in light years, remind us that the universe operates on scales both humbling and beautiful. Thank you for joining me on this peaceful exploration of cosmic creation. I hope these celestial lullabies have provided both wonder and tranquility as we've journeyed together through the birthplaces of stars. Until next time, may your dreams be filled with the gentle glow of stellar nurseries and the quiet majesty of our ever-evolving cosmos.